So last time I was talking about some connection to hypergeometric motifs. There will be still some connection, but a different topic rather. Okay, this is a joint work with two authors, so Bidisha Roy and Matija Kazalicki, and these are like separate papers, but all together it's combined. Okay, so let me introduce the main characters for this talk. So we are going to basically talk about one-parametric families of elliptic curves. So you can just basically take your favorite Weierstrass equation if you want. Of course, you can take a different model, doesn't matter for me that much. What's actually quite critical for the calculations that we are going to do is that the coefficients are actually normalized polynomials, so that we have no denominators. This is just for convenience so that I can really reduce everything modulo p. And maybe sometimes the reduction is kind of catastrophic, but it's all okay. All right, so we have the usual discriminant, and then we are going to fix for the study the prime number. Of course, we will vary with the prime number, but for every formula, the prime number will be fixed. And now I'm just taking a naive reduction of this elliptic curve modulo p as a scheme. So just think about basically this equation, just reduced modulo p. So no fancy model reduction, nothing like this, just plain reduction modulo p. And of course, we are interested in studying this bias, so the difference between the number of points on the projective line and on the projective model of the elliptic curve. You can also, if you want, at some point the formulas will just become completely general, so you can switch the prime number to a prime power. Still, everything makes sense for most of the theorems, well, maybe except for the ones that I'm going to relate to the pith coefficient of a modular form. So then you'll have to somehow modify it a little bit. And the topic of study for today is basically a sum of this form. So this is called a Cave moment of this family. So the k is an integer, 1, 2, and so on. And well, for convenience now, I'm just avoiding the places of bed reduction. In the end, we can either put there a 0 or a naive number of points that we get from the reduction, so that will depend on how we normalize these sums. Okay, so these are just, of course, these are integers, and I want to show you some results about their properties so that they come from motifs. They have actually, you can attach with each family of these objects, so if you vary with p powers actually, you can attach the local zeta function. If you vary with p, you can actually attach to this whole sequence a global zeta function. And what's difficult about these sums in general is that not much is actually known. So I'll show you some results for some families of elliptic curves, even with some positive moduli. But most questions are still pretty open. So that's probably an interesting topic for the future as well. Okay, so let me announce first the foundational theorem by Philippe Michel. So this is a result from '95. And to state it properly, it would be convenient for us to somehow symmetrize these sums. So sometimes I call this just naive moment, because you just have the cave powers, the sum of cave powers. But in a more smart way, so just to get rid of some of the influence of lower weights in this motivic sum, it's a little bit better to symmetrize this expression. And by symmetrization, I mean an expression of this form. So of course, if you rewrite everything in terms of AP divided by 2 square root of P, you can of course substitute the cosine of theta pt here. So then in the end, you just get a polynomial with the coefficients in square root of P and in the variable of A. It's just an expression which is basically equivalent. And in this form, Michel proved that if you have any family of elliptic curves, and what's important for this statement is that the J invariant is non-constant. If it's a constant J invariant, the sum is much simpler because it's essentially a character sum. So you can estimate everything independently. But if you have this non-constant J invariant, so you have this family, you can find a conductor, you can find a constant n. This is really a Swan conductor of a certain Galois representation, so you can compute it very explicitly. And then for all primes which are not dividing this conductor, and for every positive integer k, well, you have this non-trivial estimate of that symmetrized version of the cave moment. So what's non-trivial about this estimate? So the the naive estimate will be C times P. Okay, so this will be the naive estimate of the sum, and you're sparing the square root from the P. Question?
I don't understand. Why isn't it just less than or equal to C? Because C depends on P and K.
No, actually not. So
that's what you wrote. For every P, there exists a constant C.
Oh, okay. So maybe it's just my.
So C should be independent.
C is only dependent on the family itself.
Okay. So
just the family. Yes. Yeah. That's
also doesn't depend on K.
Exactly. Yes. That's actually. Yes. Yeah. That's a good point. Yeah. Of course. That would be just not intelligent statement. Okay.
But it depends on K?
No, also not asked. So there exist constants K, C, and N.
Yeah, no. C just on the family. Just on the family.
Doesn't depend on
So the theorem
K.
is there exists constant C and N.
Exactly. Yes.
Okay.
Yes. So N and C are the constants only attached to the family, and then everything else is like.
That's the power of the result.
Okay. So how the result is proved? Well, you actually interpret this sum basically as a trace of Frobenius of a certain elliptic sheaf. So this elliptic sheaf is just basically constructed from the family itself. It's just a pullback. So it's quite a natural construction. And then in this case, well, you have just three cohomology groups with compact support. So you have the index 0, 1, and 2. And so H0 vanishes because we are over the punctured affine line, so that's by definition. And now the non-trivial result that we have to use is that actually H2 vanishes, and this is a famous result due to Nicolas Katz about large monodromy groups in the family, and that's exactly where we use essentially the fact that we have the non-trivial J invariant. If the J invariant will be trivial, then the monodromy group will be small, and then you don't have the vanishing, and then actually the sum is slightly different, so you have really some kind of non-trivial leading term. So then you don't expect this kind of estimate, you actually have C times P. So it can be larger. Okay, but now the question is, okay, so we have these kind of motivic flavored cohomology groups, so we can try to study it directly from this point of view. But it's quite a difficult situation because these groups, of course, they kind of have nice motivic interpretation, but that's not much beyond the definition that we can actually do with this approach. So it just gives us a foundational result how to estimate it. As a corollary, you can explicitly now write down the naive moments in an explicit way. So you can see that the first moment is always a constant times p plus something of lower order. The second moment is always p squared plus something lower order, and so on and so forth. The leading coefficient for the first moment is actually related to the Mordell-Weil rank of the family of elliptic curves. So that coefficient has some kind of arithmetic meaning. And I'm going to show you that actually it turns out that if you properly write this sum in a specific stratification with respect to elements of appropriate weight, then all of the ingredients have very precise arithmetic meaning. Okay, so these sums have a very rich arithmetic structure, but in general it's quite complicated.
But is that theorem of Katz actually effective?
What do you mean by effective? Well, it's showing that the H2 is vanishing. That's all it's telling you.
But then
H1 is
active constant.
Oh, the constant. So if you're asking about the constancy, that's in principle computable. But you know, like if you give me a Galois representation and you ask about computing the conductor of this representation, well, it's not completely obvious how to do this. It's not a finite computation, just like an algorithm, right? I mean, you need a little bit more of understanding of the family. I'm actually going to show you results that indicate that you need to study the geometry of the self-products. So the Kuga-Sato varieties are actually behind the scenes. That's what we are going to study. Okay, so so let me tell you what has been known for a while about these sums. So this is actually a famous result that was used and proved by Deligne. So that if you have a one-parametric family which is universal, so that the elliptic surface that you get actually is covering a modular curve, and it's really this universal family with respect to this modular curve. Then you can show that the naive cave moment is a sum of the AP coefficients of some eigenforms with respect to the level that is related to the base curve that you study. And of course, the level is fixed, but the weight is bounded. It's essentially bounded by this integer k, but it can be smaller. Okay, so that's what I said, that these sums are mixed motivic, so they are mixing up motives of different weights, which makes it a little bit complicated to study in general. And if you look at the possible families of elliptic curves, this is the only case where we have a really complete or roughly complete understanding of all of these moments going across all the k's. So in all other situations, what we know so far is something about maybe k equal to 1, k equal to 2, something beyond, but not in general. So the problem is that these motives that you get are kind of getting into some kind of intricate families, but we don't have a clear picture what's the systematic point of view like in this special case. There is a separate result, which is essentially quite a deep exercise about character sums. So when the J invariant is constant, well, you can explicitly write down for every moment k, you can write down the explicit formula that you get in every situation. And there's also a very famous result due to Brian Birch, and that one is quite interesting. So if you look at the previous results, the question was to sum over one parametric family, but then what happens if you have a multi-parametric family, like you just take all the elliptic curves with respect to A and B varying, and it turns out that for every integer k, for every prime p, this formula is actually a polynomial in P, and the coefficients of this polynomial are actually related to the traces of the Hecke operator at P. So that's a very nice result, I think proved in the 68 or 69. And this is, again, essentially using the property that you have this large monodromy group. So it kind of tells you that if you study these moment sums over something that is bigger than one-dimensional, you expect this sum to be polynomial. So there is no obstruction in a sense in this sum.
So I'm lost to the one. So let K be 1.
Yeah.
Isn't MP1 is not just AP1? I forgot the definition.
So this is the sum of AP over all elliptic curves with varying A and B in this case.
As you're summing over A and B.
Yes.
Oh, you didn't write that.
That's it. Yeah, sorry, in this case, yeah, that's an abuse of notation in this situation, but this is the only case that I'm going to use it. So what I meant by this case is that you're actually taking a sum over all A and B and then P.
It's short, but I'm fine, yeah.
And then the AP of that. With the K power. So this, of course, generalizes. So if you have more parameters, you can specialize to always Birch, and you expect to get a polynomial. So, and beyond that, so if you have a really an interesting case is when you have actually one parametric families only. Of course, you can generalize also to sums where you sum not over P1, but you can also sum over a curve. But that becomes actually quite complicated, and I don't know of any single result treating this situation.
So we do know that they're not polynomials, so we don't expect them to be polynomials.
Well, I'm going to show you like now a series of results when they are polynomials, they are not polynomials, and they can be anything in between essentially. Okay, all right. So this is a nice exercise. So you can think of this in your mind how to prove it. So if you have a singular cubic, okay, that changes a little bit the situation. The cave moment now of the singular cubic is actually 2 to the power k minus 1 times p minus 1. That's an easy exercise. You just use the fact that you can parameterize the singular cubic in an appropriate fashion, and then you just rewrite everything in terms of the AK. So that's an easy case. Okay, so the singular cubics are definitely not interesting. Okay, but now let me give you some prior results that were studied by people over several recent years. So this is a typical situation which people have encountered so far. So you have like some basically a random one-parametric family. This is the rank of the Mordell-Weil group over Q of T. And then, of course, you can compute something about the first moment. These are all rational elliptic surfaces, so that's pretty much a straightforward calculation. But then you immediately get stuck with the second moment unless there is some kind of symmetry happening with the summation so that something cancels out. If it cancels out, then you end up with kind of an explicit formula, but this is what I consider the degenerate case. And more typically, you end up with a summation like this, that you have some piece of the sum that is kind of beyond understanding, so you don't know how to interpret it motivically. And this is what you can get if you attack this problem just straight on from the definition.
Formed in red, I assume you don't mean x cubed minus x squared plus x over p with the Legendre symbol.
It's, yes, exactly.
So
yeah.
this is just AP of the elliptic.
Yeah, exactly. So this is just hiding the fact that we don't understand the sum. I'm actually going to show you that.
It is AP of the elliptic curve, so why don't you write it?
Well, the point is that
Legendre symbols.
the point is that you can extract some data from the sum, but then you get stuck with this part, and then you're done. So this is just telling you that.
Then this is just the definition.
Yeah. I mean, this is actually the simplest case. I think I don't even cover this case. So this is the simplest case of a family for which we have no idea what this sum on the right for the second moment should be. I mean, this is probably the simplest case that was never covered by any statement. It's not a universal family, so you cannot use Deligne. It's one parametric, so you cannot use Birch. And also our theorems are not covering this case. So I think this is the simplest case that is still pretty much open. Okay, but let me give you now some positive results. So this is one curious situation that came out as a byproduct of a more general consideration with Mattia. So we noticed that, well, in the end, that if you have this family, so this family is not universal, you can show that it's definitely not equivalent to any universal family, but it's kind of not far, really. Then for every odd prime, we have the following result, so that the second moment is p squared. That's exactly what Michel tells you, but now you have the coefficient of the modular form, which is actually a unique rational new form of weight 4 for the level gamma 0, 8. And then the remaining term is actually coming from I would say a finite scheme, so it's much simpler to understand. Okay, so how this result is proved? So this result is actually proved by cleverly counting points on a certain threefold, and it turns out that in this threefold we have a way to understand the number of points in two different directions. So one direction is basically given by slices which are rational elliptic surfaces, okay? So that gives you one way of counting points. And the other direction gives you a fibration in K3 surfaces, but they actually have Picard rank 19. And if they have Picard rank 19, then they have like a three-dimensional, in the cohomology, the second cohomology, they have a three-dimensional piece that is related to the self-product of a single elliptic curve. And that's exactly this elliptic curve that you have here.
Why did you write it as a Q expansion, not as a product of eta?
Oh, I knew that you would ask about this. It was just element.
He wants the p coefficient.
Yeah. Well, you definitely can in this case do this. So that gives you also kind of an intricate identity about this sum, right?
Do you know a priori what the weight filtration variations are?
Yeah, I'm going to tell you. Yes. Yeah. So somehow, so in this case, there will be another result in a moment. So you can either get a modular form like this of weight 4, or you can actually get p times the bias of the genus 2 curve. These are the only two possibilities that essentially can happen, well, unless we know some strange motives we don't know so far that could appear in this weight, but that's something that is, I think, kind of conjectural. Okay, now a little application of that kind of formula. So with the techniques from this paper and basically with this result, now I can prove statements about modular Calabi-Yau threefolds. So this is kind of an example. So recently, Bert van Hemmen and Dino Festi, they found experimentally that the number of points on this Calabi-Yau threefold is governed by the coefficient of some, probably, that's what they computed up to primes up to 100, by a unique new form with respect to the level gamma 1,6.
Wait for.
Wait.
This is weight 4. Yes, that's still weight 4. And so the usual way of proving this kind of result is basically you apply Faltings-Serre method. You compare the two sides up to some ridiculous bound, and then you conclude by the principle of showing that many traces are enough to show that two Gauss representations are equal. You prove that they are equal. In this case, I have an actual direct proof by correspondences that this threefold is really modular, and we can go beyond that in several cases which are related to self-products of elliptic curves. I think it's a genuinely first proof of the modularity that is not using, for Calabi-Yau threefolds, there is not using any kind of direct comparison or any kind of very special CM trick or something like that. Okay, and here's another kind of result, quite recent, that we found. So, for example, the Legendre curve, well, it's not far from being universal, but it's not exactly a universal curve.
So what is universal?
Sorry?
What is universal?
So universal means that, first of all, you need the reduction types to be multiplicative. And in this case, you have an additive
No,
family.
but I don't know what it means.
Oh, so by universal, you mean that you have a family of X.
Over
Yes, yeah, something like that.
But I thought Legendre family
It's gamma
is the
gamma
archetype
2,
example.
Yeah, but it's not, I mean, it matches, but the problem is that the level is too small to have this kind of, how it's called, the fine moduli scheme. The moduli scheme is not fine, so everything is up to twisting. That's the problem with this family, also with Clausen. So these are like families which are not far from being universal in the strict sense, so that everything is like pullback from that family. It's up to twisting, and that twisting causes a lot of problem because in the summation you cannot use Deligne. So for the proof you actually need a correspondence.
Isn't it, Mr. Kugas? I mean, if you write T to
No, actually,
the
this.
help note, you'll forget Lambda time.
Well, it's Kuga up to twisting, because the level is 2. So 2 is the level that is. I mean, the problem is that minus identity is in the modular group. So that means that you cannot distinguish in the family between the curve and the twist. And that's in the sense of Katz and Mazur, this is not a fine moduli scheme. So then the family that you attach to this is not universal. I mean, it's universal up to twisting. And there are only 4 families of this kind, and they happen all to be actually hypergeometric. So that's a kind of a funny coincidence that all of them are hypergeometric. The indication that they are not fine moduli schemes is the fact that you have in the reduction type, you have something that is additive, not potentially good. So you have I0 star in this case, or you have 3 star, 2 star, and 4 star. That's why it's not completely trivial. Any more questions? Okay, so in this case, what we proved is that any moment is actually related to the trace of the Hecke operator on the modular forms. Depending on whether k is even or odd, you have some kind of correction. And for Clausen family, it's kind of similar, but there is a little star here because we are struggling a little bit with the odd case. So this is for the even moment, but for the odd moment, there is some Hecke character that appears that is still not completely under control, so we don't understand yet the full picture for this situation. Okay. But in a sense, this result, you can always say that you can relate it somehow to the work of Deligne, and that's the whole point. So you can re-express, so in the case of Legendre, you do an isogeny to another curve, and then you actually reparameterize something cleverly, so that you relate to the curve with level 4. And then when you're on level 4, you actually have a fine moduli scheme, so you can use Deligne, and that's exactly how this result is actually proved. Okay, and very similarly, so if you consider all the hypergeometric equations with parameters beta 1, 1 and alpha, which are rational, that come from one parametric families of genus 1 curves, that's a complete list. That's a nice exercise in this zigzag method that I think Fernando can explain to you in more detail. And in every case, it happens that all the moments are essentially modular. So in this case, we are actually using a result due to Jerome Hoffman, which is still, I think, under production. So our result is conditional on their paper. So we have to critically use some of their tools. But in the end, you get formulas which are completely sound. And in every case, you can notice that you get modular forms of different levels, 2, 4, 9, and 36. And beyond that, there is nothing that is modular. So this list completely ends up all the connections with modularity, except if you have a family that by isogeny is related to something that is universally modular.
Sorry, what do you mean by modularity of moments?
So I mean that,
of TP?
so that you can express the moment as a combination of APs or traces of Hecke operators of classical modular forms. I even have like an unofficial conjecture, but I would say more a question, that if you ask for the converse, so that you expect all the moments to be related to modular forms, it ends up in this list. So there is nothing beyond that.
So modularity means trace of TP, or
Yes.
just some set of forms such that their coefficients govern?
Well, I think you should probably, well, I don't think it's possible that you just have a subset. I mean, I can imagine a situation.
You had such examples.
No, but this was actually coincidence because the dimension of the modular form space was 1. So that's why the trace of Hecke was exactly this AP. So that was actually, I mean, this was just a consequence of having low level. If low weight. In the higher weights, well, this goes beyond. But by the way, for this case, so for this specific family, we have no proof beyond moment 2. So if you ask me about the third, fourth moment of this family, I don't know. I mean, this is a purely geometric construction.
You can conjecture that.
No, absolutely not.
So you aren't saying that the motive splits into left-sided pieces and modular pieces. You're saying
yes.
You're not saying that.
No, not in general. Not in general.
In this case.
Well, I tried, like the third, fourth moment, tried like to search to LMFDB for any kind of nothing. Nothing matched this kind of pattern. I think it's interesting because, I mean, it's basically a question like if you have a Kugasato variety for the double self-product and you get a modular motive, do you expect that the triple self-product will be also modular? I'm not sure. This is in general, it's a likely outcome.
So will this be a test of the
Yes.
the group is a non-congruent?
Yes. That's what I expect. That beyond the second moment, you should get. I mean, I don't know. Maybe in some kind of like generalist sense, you can expect some kind of like symmetric power operation on the motive. But I don't think it's definitely not giving you any known modular forms. So beyond this second moment, we don't know anything about even this single family.
That's a very stupid question. Maybe I just forgot, but why doesn't the left-hand side depend? It's the family. What? I didn't understand the definition somehow.
On the left-hand side, so let me just write the definition again. So M to P is just the sum over T and FP or P1 FP. Okay? So,
Oh yeah, it's the sum.
yes, it's always a sum.
So it's not MP of ET, it's just bad notation.
Yeah, ET is an indication of the family. Yeah, it should be like with the bracket. Yes. Okay. All right. So let me give you now quite a general result that we recently proved. So so I'm going just to modify a little bit the notation just to make something the sum more symmetric. So I'm adding also the contribution from infinity, right? So far I was just adding over the fibers over A1. Now I'm doing the same summation over P1. Okay, and now we have the result that tells you that if you have a pencil of cubics, kind of a general one, if it's not general, we also have a result, but it's ugly. I mean, you kind of have like 20 different cases which specialize to different scenarios, but I think this one is probably the most elegant. And now you can prove that, oh, that's, sorry about the switch in the notation, so that should be M2P. I think I just swapped it yesterday when I was doing notes. So the second moment of this family is actually P squared, that's Michel. But now you have a new ingredient, so before there was a modular form of weight 4, now it's actually P times dP, where dP is the bias of a certain explicit genus 2 curve. Okay, so basically what it's telling you is that the motive associated with the sum is actually the motive of the Jacobian of a genus 2 curve. Sorry?
It's a tail twist.
It's a tail twist, yes. Yeah, that's why you multiply by P. And then you have also the contribution from a finite scheme. And this finite scheme is basically just a polynomial of degree 4. So it's very concrete. Here is actually a concrete result. So if you just take two polynomials which satisfy these typical conditions, so this is the family that you have, and now this is the result. So if you sum up all the APs squared over T over P1 FP, you get 5 ingredients. 2 of them are completely trivial, so they are 0. F4 is actually equal to P squared, and then F3 is connected to this genus 2 curve, and F2 is just the number of roots of this quartic polynomial. So if you give me any numbers, I can compute in Magma exactly the equation of the curve. It's not difficult, it's just a quotient that I have to compute. What's a little bit difficult is that if you ask me in general, so you give me like general polynomials of arbitrary coefficients, I have some issue with computing the model. The model is just having too many coefficients so that I cannot handle in Magma like everything in terms of moduli space, like write it arithmetically, right? So if you give me like one parametric family, that's fine, but if you give me like a family with all full 8 coefficients, it's kind of a hassle to write it down, but every single case explicitly, independently is possible. Now, when you also count the moduli, so what's the moduli space of these cubics? So generically, this is an elliptic surface which is rational. It has the trivial contribution of the second homology group, which is 7-dimensional. So by a result of Remke-Klustermann, the moduli is actually 3-dimensional. Okay, so the moduli space of these cubics is actually 3-dimensional. But now on the right, you have the moduli space of genus 2 curves, which is also 3-dimensional. So it's essentially a 1-to-1 match. So you can expect that in general, if you give me a genus 2 curve of your choice, in principle, you should be able to find the P and Q polynomials, but of course it's an arithmetic problem, so there could be some kind of arithmetic abstractions over a particular prime to realize that. Okay, all right, so let me now tell you about the proof of this statement. So here's a general comment about the L function of this moment now. So if you take the moments with respect to the prime powers, well, you can package everything into a formal zeta function, and you have actually proved, this is essentially Dvorak plus Deligne, that this zeta function is really irrational. It's basically following the proof of Michel in detail, plus the classical ingredients.
In the form that there's a k on the right and no k on the left.
Yeah, but that's exactly the point. Oh, sorry, no.
Something's missing.
Yeah, the k is missing on the left, sorry.
And where should it be?
Sorry?
Where should it be? It's mk.
Yeah, k,
So
there
it's
should be a
still
k.
k.
Yes.
Huh? No, you can't exponentiate the kth moment, surely.
What do you mean?
Well, I don't know what's on the left, but it seems very odd to fix a k, take the kth moment.
Well, you were varying with the p power.
Otherwise, it wouldn't be rational.
So you're adding with respect to the p powers here, and the k is fixed. The k is fixed. So for every k, you have a different zeta function, and I mean they are like all independent, right? That's what I said, that the motives for different k's are like somehow
So it's just
completely
somewhat.
Yes. Okay, but now this approach tells us that we can decompose precisely every k moment in this kind of sensible way. So the stratification is with respect to the algebraic numbers of the same motivic weight. And we are going to study this separately. Okay? All right, and now, as I mentioned, so the general problem is quite specific because we are in the situation that we have this finite field mixed motivic situation, so we are mixing motives of different weights. And what is known about this case? So not much. I mean, the first moment, basically already the first moment, so if you have rational elliptic surface, then the first moment is completely explicit. You just use a Schrödinger algorithm, and you can just write down everything explicitly in terms of Artin representation, so that's really efficiently and effectively computable. But already for K3 surfaces, so if your one parametric family is a K3 surface, the total space, then you can only so far something about high Picard ranks. That depends on the transcendental motive, which can be general automorphic. Well, in the general case, even of the first moment is very hard, and even beyond that gets even more complicated to study. And okay, and one other application of these sums is to prove that they actually have a certain bias. So now, if you write down, for example, what did I do? So if you write down now this motivic decomposition of the sum, and you compute the appropriate average of the normalized coefficients, then it turns out that we either have that this average is 0, if you go from the left, or if it's not, the first average should be negative. This is called the bias conjecture. And so this is in more general formulation of the same. And we actually do prove it. So Miller asked it as a question if this is really the case, that these averages are either 0 or the first one is negative. And by this result about the family of cubics, we actually proved that this is the case, at least in this situation, for an infinite family of elliptic curves. So this is the first instance of confirming this bias conjecture in going beyond just single example. And the bias is actually between -5 and -1. The deeper reason for studying these biases is related to the thesis of Stephen Miller, where he was studying some Dirichlet series related to elliptic curves, and that was somehow a question that emerged from this consideration. You can also study the Satote distribution. These are also quite interesting in general, but quite inaccessible beyond the cases that I have announced so far. Okay, so let me now get back for the rest of the talk. Let me explain to you now how this is actually proved. That is already quite involved. Okay, so all right, so let's fix the notation for the family. So this will be just a pencil of cubics, and we want to relate the point count on a certain threefold to the second moment. And what will be the threefold that we take? So it's a threefold which is basically a total space of the family of Kummer surfaces. So you basically take the product of this elliptic curve itself in two variables. So you get a singular threefold. You can make a closure of this threefold by assigning the infinite fiber to be exactly of this form. And now it's not difficult to glue all of this together, so you actually get a proper threefold. It's still singular, but that's okay for us. Okay, and now you notice the obvious observation, so that the number of points on this compactified threefold, which was just a total space of the Kummer self-product, is actually equal to q cubed. So this is for any prime power, any characteristic, even 2. For 2, actually, this term completely vanishes tautologically, and otherwise, this is non-trivial. So the number of points on this threefold is q cubed plus q squared plus the second moment. So if we have any way of computing the number of points on this threefold that is going beyond the definition, well, that will be our proof. Okay, and now a certain miracle happens. So we learned about this miracle actually after we proved it. I mean, just someone pointed to us that actually this is not such a complete miracle. So if you look at the literature, and especially in the papers of Bovill, there is a certain notion of understanding of this motive of certain threefolds. And in this case, the magic that happens is that the third motive can be, in our case, related to the prime variety associated to the pair of curves. Okay, so I'm going to explain what this pair of curves is. But the punchline is that basically, since the model that we have, so the model is quadratic in K, well, you have another way of fibering this threefold with respect to x1 and x2. So if you fix x1 and x2, it's just a conic bundle. Okay? And if you have a conic bundle, you have two curves. One is the curve of the singular locus, that's going to be called delta. And then you have the first Fano variety, which is the variety that controls the slopes. Okay? And this will give you a genus 3 curve. So the genus 3 curve covering a genus 1 curve, that's the situation where you get a prim variety. And the prim variety is, the dimension of this prim variety is actually the difference between the genera, so it will be a genus 2 situation. But it turns out that it's not exactly the Jacobian that you get, so this intermediate Jacobian is actually not a Jacobian itself, it's a prim variety, but it's isogenous to something that is principally polarized. So in the end, we end up with a proper genus 2 curve that is actually expressing our motive directly. Okay. All right, so let me tell you a little bit more about the details for the proof. So of course, the curve delta, so the singular locus of the conic is just explicitly this formula here. Well, it has a component which is uninteresting. So you have to divide this by x1 minus x2, right? Because this is the situation where we are not interested in. And now, when you take the slopes of the conic, okay, well, you end up with this curve. So the curve C now is naturally covering delta, and when you remove from delta this component of x1 equal to x2, the pullback of this is the curve C tilde, and generically it will actually have genus 3. Okay? All right. So now this gives us a way to count the number of points. And this is just a reminder about this theory of prim variety. So if you go to the book of Mumford, you can find that indeed you expect a motive of something two-dimensional. It's not, the polarization of this abelian variety is 1, 2. So this is not a Jacobian. So that means that in our proof we have to do something to actually prove that there is a genus 2 curve associated with this motive. And that will be actually done over a finite. Okay, so let me show you now some details about the calculation. So, okay, so we write everything explicitly in terms of the curves that we are interested to study. And in particular, well, you can show that now your second moment is expressible in terms of the difference of the number of points on these two curves, and something that is related to just a finite scheme. Okay, so this is the easy part. Now this is the hard part. And now in general, you don't expect that the difference between the number of points will be actually the number of points on another curve, right? So you need some kind of extra symmetry to prove it. And it actually happens in this case. So first of all, we prove that geometrically these curves are irreducible. So that's this typicality condition that I have to impose. If they are not geometrically irreducible, then the final motive is either elliptic or elliptic plus a line, so it decomposes. It can decompose into something much simpler. But in the end, you get proper curves of genus 1 and genus 3 with proper smooth projective models. The difficult part about this step is to actually show the resolution of singularities, because you have to do it over the whole moduli space. So I take all the polynomials, and then I have to really resolve the singularities, and that takes a couple of pages to do, but eventually it's a finite calculation, quite tricky. Okay, so we end up with this conclusion now that the second moment now is Q, of course, times the difference between the number of points on the smooth regular models of two curves, and then there is this degree 4 scheme that is just in disguise the same guy as was here. So this is the quadratic character, okay? Quadratic character modulo 3. Okay, so then to finish, we have to study the geometry of this cavern. And it turns out that it's actually very nice because this Fano variety of the slopes, it's actually a genus 3 curve which has quite a rich group of automorphisms. So at least some subgroup of the automorphisms is generated by these three. So you have 3 involutions, so that the total group here has 4 elements. So 2 of these involutions generate this subgroup. And now I want to produce all the quotients of this genus 3 curve. So of course, if you take the quotient with respect to the first involution, you recover the curve delta, right? So this is the double cover from C to delta, from genus 3 to genus 1. The cover with respect to the whole group is actually genus 0 curve. So that's also quite convenient. And now when you do the point count, so you're using just the orbit lemma, you can prove that the number of points on this genus 3 curve is plus the number of points on the total quotient is equal to the number of points on the curves which are subquotients with respect to every involution separately. By the way, so this lemma is proved completely elementary. You just count the number of points in the orbit. But it turns out that it's actually a finite field analog of a famous theorem due to Acola. So this is a special case of this theorem. If you take a curve with the automorphism group Z2 plus Z2, this is a complex situation. So this theorem is just in complex analytic setting. But there you actually get the information about the genera of the curves. So indeed it matches because the number of points on the curves compared to the genera is connected by the Jacobian, right? So if you compute the Jacobians of these curves, that's exactly what you would expect. But it turns out that actually it's not enough to have this theorem. So you cannot conclude from this theorem this point count. You actually have to do something directly. Okay, so I still have like 5-10 minutes. Pretty good on time. Okay, so now you do the calculations. So apart from characteristic 2, but as I said, for characteristic 2, the sum, the second moment just vanishes, so we don't care. And away from characteristic 2, you can prove that the genera of these subquotients are 0, 0, 2, 1, and 3. So this is the curve that will appear in the main theorem. Okay, this curve of genus 2. Okay, and now since we are in the bi-elliptic and even hyperelliptic case, because the C bar curve, this genus 3 curve, is actually hyperelliptic even. Well, you can now show that the difference of the points on these two curves that we had from the definition is actually the number of points on this curve C2. Okay. So now there's a miracle that happened because we actually showed on the level of finite fields that this is exactly how we construct the motive attached to the second moment, right? I mean, otherwise there would be no access to the motive, right? You could try to do this theory of Beauville, but still you'll end up with some troubles because the model that you get is singular, so you'll have to first resolve the singularities. But we do it on the level of curves. Okay, so now if you put everything together, well, you end up with the final result. So indeed, the second moment of this family of cubics has the motive, the non-trivial motive that it has is actually related to the Tate twist of the genus 2 curve that somehow appears from this Fano construction. Okay, all right, so now how about this bias conjecture? Well, now we can update this, so we don't need the full strength of the Sato-Tate conjecture for genus 2 curves to prove that the average of this term is 0, so we need a little bit less, so this is unconditional really. And of course the average of the final term, so I remind you that this is just a degree 4 polynomial in disguise, well, you can prove that this is positive by Chebotarev theorem. Okay? So indeed, the bias conjecture holds, and now the value of the bias depends strictly on the average of this term. So it's between -1 and minus 5. Okay, and I think this is all that I wanted to say. Thank you very much.